This video is about trigonometric substitution for integrals. As always, begin by reading through the textbook and taking some careful notes, but now consider the following highlights for this topic. Let's begin by recalling something that is hopefully familiar to us, and that is the Pythagorean theorem. Typically introduced in earlier algebra or geometry, but the Pythagorean theorem states the following: for a right triangle, which we have here drawn. A right triangle, of course, is a triangle with one right angle. And I'm going to label it in the following way. So I have the corner in the bottom right of my triangle labeled as the right angle. And then, of course, across from the right angle, you will always find the hypotenuse, the slanted side, which I have in my case. In the bottom left corner of my triangle, I've put an angle label there as theta. We'll see later on why that can be useful. But for now, let's do the following. If you recall that it labeled is that I'm going to say the bottom leg, the horizontal leg, is just a letter A, lowercase letter A. And I'll call the vertical leg going up the right side of my triangle, lowercase b, and then the hypotenuse, lowercase c. And you may use different labeling schemes, but you'll need to be clear when you're writing out the theorem with whatever you've used in the following way. So we know the theorem, the Pythagorean theorem, states that if labeled as I have, we could say a squared plus b squared equals c squared, and that is where a and b are two legs of the right triangle, and then c, importantly, is the hypotenuse. Again, that's always across from the right angle. All right, so we know that's true, but then notice you could do a little bit of algebra with that, which you may or may not be motivated to do at the moment. But if we solved for c in this equation we just wrote from our Pythagorean theorem, and we would do so by taking the square root of both sides, then this would imply that c equals the square root of, if you take the square root of the other side, you'd end up with the square root of a squared plus b squared. All right, we're just going to leave that there for a second and note a couple other possibilities. So if we take the exact same situation, that is this original Pythagorean theorem equation, but this time let's solve it first for a squared. If I were to get a squared all by itself, wouldn't I just subtract the b squared from both sides and end up with a squared equals c squared minus b squared if I've subtracted b squared from both sides? And then if I wanted to solve for a in that form of the equation by taking the square root of both sides, I'd end up with a equals the square root of, well, c squared minus b squared, the other side of this second equation. Okay, why we might talk about all this will come into play shortly, but let's do one more iteration here. What if I wanted to, again, take this original Pythagorean theorem equation of a squared plus b squared equals c squared, and this time first solve for b squared. Of course, that would happen by subtracting a squared from both sides, which would leave us with b squared equals c squared minus a squared. And then again, if I wanted to do something similar that I've been doing, that is solve for just b instead of b squared, by taking the square root of both sides, I'd end up with b equals the square root of the other side of that equation, which would end up being c squared minus a squared. Okay, there's a lot going on with this theorem, but I want to now put it all kind of back in place and start to see eventually why these expressions would matter. So if I go back, knowing I labeled the original hypotenuse as c, but then I solved for c using the Pythagorean theorem to get that c equals the square root of a squared plus b squared. I'm going to label a new triangle, another right triangle, but instead of c, where the hypotenuse was, I'm just going to replace that with the expression we got for it, which is the square root of a squared plus b squared. Again, we found that directly from the Pythagorean theorem equation, and now I'm just replacing the hypotenuse label of c with what that equals. Now we're going to do the same thing with the other sides as well. You'll notice, let's see, for B, I'll go in order. For A, which I had labeled as the bottom leg of my triangle originally, we figured that A is equal to the square root of C squared minus B squared. So I'm going to replace the label on the bottom of my right triangle, which was originally just given as A. I'm going to replace that with the square root of the quantity C squared minus B squared. Again, that's what we kind of found A to be if we solve for A in the Pythagorean theorem. And then thirdly, as you can probably guess by now, we'll take the side B that we originally had as that vertical side on the right. We solved for B, and we can now replace that with the square root of C squared minus A squared, as we got when solving for B from the Pythagorean theorem. Okay, so why do we care? Well, this is, I think, a helpful way to understand what we're going to try to do ultimately in this topic. So what we've just now kind of written, I'm going to box in. It's a triangle that's just labeled with all of these sides. But I want to make a big deal about this triangle because I think this is a very helpful way to understand everything we're about to do. And without this, it's not that there are no other ways to look at it, but I think it's a lot more challenging. So I think this is going to be our useful little formula or scheme for understanding why and how we get some of the next coming formulas that involve trigonometry and eventually calculus. All right, let's move on a little bit and recall some other things we'll need. So specifically, how about some trigonometric ratios that may be familiar to you? So what I mean is sine of theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, or tangent theta equals opposite over adjacent. You may recall these from trigonometry. A helpful memorization tip you may have even heard is SOHCAHTOA. Just a way to remember these. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. We need to be pretty familiar with those, as you'll see soon. But then also recall any previously known, used, and memorized trigonometric identities, derivatives, and of course antiderivatives. We'll be using those as needed. Speaking of recalling, let's also note a couple that should be somewhat familiar to us. The antiderivative, or the indefinite integral, of 1 over x squared plus 1 dx is equal to arctangent x plus c. That shouldn't be too surprising, and it should be somewhat recognizable, if not familiar. Or secondly, the indefinite integral or antiderivative of 1 over the square root of 1 minus x squared dx is equal to arcsine x plus c. And again, these are just some hopefully familiar things from really Calculus 1. Now, though, what about something that is unfamiliar? Again, assuming those previous examples are somewhat familiar or could be familiarized if you forgot them. But what about something that's unfamiliar, like the following? So what about the integral, the indefinite integral or antiderivative for 1 over the square root of x squared minus 1 dx? Notice the difference. We did recognize, hopefully, 1 over the square root of 1 minus x squared. But what happens if you switch the order of those terms? And now it's the square root of x squared minus 1 in the denominator. Do we have an integral for that we understand or recognize? Or, for example, what about changing what's under that radical or that square root to be x squared plus 1? Well, if you comb back through your calculus, you will find that we don't have anything known that matches those so nicely. And so our goal now is to find a way around that. Now let's note or observe the resemblance of the radical expressions in these unknown integrals. So what I mean specifically is, let's see, I'll highlight this. These radical expressions in these unknown integrals I just stated above would be the square roots containing, these are in the denominators, right? The square root of x squared minus 1 or the square root of x squared plus 1. Those are unfamiliar to us, but notice or observe the resemblance of those radical expressions in those integrands, in those denominators, with radical expressions that we observed in, I'm just going to refer to it with the same little star symbol above. Okay, so what I mean is if you scroll back up, you will find that I starred, remember the second right triangle we were constructing using the Pythagorean theorem, and we replaced A, B, and C with their radical equivalents, those root expressions. Notice some resemblance in those root expressions with what we're now seeing in, say, these denominators of these unfamiliar types, right? That's kind of what we're going to try to leverage or use to understand how to get through what is previously unfamiliar to us, but I think now might be doable with all of this in mind. Or we could say the big idea of this topic is that we will use a trigonometric substitution to combine what we know above from the Pythagorean theorem in that diagram and trigonometry to create an integral we can evaluate in some of these unfamiliar setups. I referenced a couple here above just shortly before, and there are many others. So we'll see how now, if we can use the trigonometry of the Pythagorean theorem as well with our known identities and derivatives, I think we can actually go a lot further. Now, in order to help us do this, I'm going to use a right triangle model for this. This is not the only way you might see this presented, but typically reading through any textbook that does a fair job on this, you will eventually see some kind of right triangle diagram. I'm going to kind of use that as the backbone of how we're going to discuss this, and here's what I mean about that. So we're going to start by saying that let's let A be some constant, that is some positive constant greater than 0, and let's let U be some function of x. I'm just picking out some variables to use to make this all look a little bit simpler. So first, for integrals involving the square root of a squared minus u squared. Again, doesn't that kind of resemble some of these roots we've been seeing? If you look up at some of these unfamiliar integrals, or even above at the Pythagorean triangle relabeling I did, you'll see some similar looking things. And so first, our first model is when you have integrals involving this square root of a squared minus u squared. Now, I'm going to draw a diagram illustrating this, and this will be a right triangle oriented just like the one we drew above in our Pythagorean theorem work. And I'm going to label the sides accordingly. Now notice I have theta labeled in the lower left corner, this acute angle of our right triangle. I'm just going to keep that there for reference. We'll be using that now. I have the right triangle labeled in the bottom right corner. And then the following. So if you orient the labeling of the triangle in this way, the Pythagorean theorem works. Remember how we're using, in this first case, integrals involving the square root of a squared minus u squared? Well, that's going to end up being that bottom horizontal leg of our triangle, the square root of a squared minus u squared. If we label it that way, then the Pythagorean theorem would indicate or demand that the vertical leg would be just the letter u, and the hypotenuse would be the letter a. That is, a our positive constant, and u our function of x, some form of x in it. So that labeling scheme will help us out, and this is only the first case out of the 3 we'll be seeing here for these models. These really will, it'd be very helpful to memorize these, and I realize that at first can seem a little daunting. Really, memorizing can be, just by rote rewriting and memorizing and flashcards or whatever it might take, Or it can be that plus practice. I like that latter method of just actually using. I think it's a lot easier to remember stuff when you're using it for something with practice. So kind of do all the above, but definitely memorize these models. There aren't too many of them, but they're very helpful. Well, let's bring some trig into this picture. For ratios involving u and a. Now, what are u and a? Again, those are sides of our triangle. We have in this first model, a is our hypotenuse and u is our vertical leg as labeled. For ratios involving those, and of course our angle theta, which is our acute angle labeled in the lower left corner of our triangle, all we're going to use is our basic SOHCAHTOA. So think about this. If you're orienting around the angle theta in the bottom left corner, that means that across from it, where our vertical leg u is, that would be the opposite of theta. And then, of course, a, being our hypotenuse, is the hypotenuse, no matter which angle you're talking about. So if you're talking about opposite and hypotenuse, then we can use a familiar friend. The sine of theta is equal to opposite over hypotenuse. And so for our model here, that means sine of theta is equal to u, the opposite, over a, the hypotenuse. And so that becomes a relative or a relevant formula given this triangular model we're now using. Now, how we're going to use it? Well, we'll see that come into play when we get to some examples. I just want to make sure that the basics of this model are at least believable at this point so far. For ratios, secondly, now for ratios involving the square root of a squared minus u squared and a. Notice in each of these cases we're pairing the expression that involves u with just the side that is a. Okay, you'll see why that becomes useful when we get to the examples. But for ratios involving the square root of a squared minus u squared, remember that's kind of the model we're in right now for integrals involving that expression. If you want to make a ratio involving that expression and the side a, well, again, notice in our triangle where we have theta in the bottom left corner, this time the root in the bottom horizontal leg would be the adjacent side in relation to where theta is. It's right next to it. And again, going back to trigonometry, adjacent is one of our three useful side labels for these trig ratios. So, with that being the case, cosine of theta, again with SOHCAHTOA, ca, C-A-H, cosine is adjacent over hypotenuse. Well, if adjacent is the square root of a squared minus u squared, then that would be that square root all over a. That's just adjacent over hypotenuse. And my goal is to make this recognizable and not intimidating. When you see these hopefully familiar looking trigonometric labels and ratios, that's my goal, to make this seem like, okay, there is some familiar stuff here. I just got to practice and see how it all comes together, but it does at least seem doable in some way. Now that's just our first model. How are we going to use it? Well, again, we'll see that shortly. Let's go on to the second one. We only have three. So secondly, now for integrals involving the square root of a squared plus u squared, notice that's a bit different. We had a squared minus u squared in the first model. Now we have a squared plus u squared underneath the radical for this second model. In this way, notice that our triangle ends up a little bit different. So we still have a right triangle model where it's oriented in the same kind of way. We have a right angle in the bottom right corner. We have a theta in the bottom left corner. And then, of course, according to necessary labeling conventions and what a triangle is, across from the right triangle you would find the hypotenuse. But this time, the hypotenuse is labeled the square root of a squared plus u squared. Now, at this point is sometimes when people start thinking, okay, sure, but how would you know which model you're using, and how do you know where the root goes? I see it in the hypotenuse in this model, but it was in the horizontal bottom leg in the previous one. How do you know? Well, again, now let me refer back to what we said originally above, and I'll try to highlight some of this. Notice the following. When you have an a squared plus u squared underneath the square root, That ends up in this model as the hypotenuse, and for the moment you may just be taking my word for it, but now go back up to where we started with all that Pythagorean work. Notice that in the second right triangle where we labeled all the sides in their radical or root expressions, only one of them had a positive or a plus in between the terms that are under the root, and it was the hypotenuse that was labeled the square root of a squared plus b squared. So there's a helpful little tip here, and that is remember that the hypotenuse is the only one that can have the plus sign between the two squared terms under the root. And if you're not convinced of that, just look back at the work we just did initially to set up this model. You're not going to get a plus between the terms for the other legs because of the algebra involved. If you're solving for them, you simply just don't get a plus sign between those terms, but you do definitely get that when solving for the hypotenuse, as we did. So I want to connect all that because that helps hopefully identify what you're working with when you're trying to sift through your tool bag of, in this case now, right triangle models to memorize for these trig identities and trig substitutions. All right, so we have this plus sign between the terms. Let's just take note of that as we did. But then notice you have on the horizontal bottom leg, we have that labeled just A. On the vertical leg on the right side, we have that labeled U. Of course, our right triangle, our right angles in the bottom right corner, our theta angles in the bottom left corner, and you can double check all the algebra. It should work. A squared plus U squared equals the hypotenuse squared. It's all held together with the glue of the Pythagorean theorem, as we saw above. If we now want to find a ratio involving U and A, which, by the way, is exactly what we did in the first model. We wanted a ratio involving U and A. Same thing here, but now, because of the different labeling of the triangle, notice you're going to have a different ratio. This time, if you're talking in relation to theta, then all the way across from theta, where we see the vertical side U, that would be the opposite. And then A, notice, is right next to theta. It is on the bottom horizontal side. So that would be the adjacent, which means we have a new label for those sides, A and U. They're different than they were in the first model. And that's important to note. Because if you're trying to create a ratio of using trig involving the opposite and the adjacent, there's only one trig function that does it, and that is tangent. So we could say now, tangent of theta equals opposite, which is U, over adjacent, which is A, again in this current model diagram, which means we have a trig ratio. Moving on, if we wanted to find a ratio involving the square root of our expression a squared plus u squared and A, then again, where those are labeled now is different than where the root was labeled on the other sides in the previous model. So this time, to involve both the root of a squared plus u squared and A, in our model, we know that A is already the adjacent side in relation to theta. And of course, the root, this time, is the hypotenuse. That is the square root of a squared plus u squared. So, of course, if you want to involve those two sides, adjacent and hypotenuse, then you have to use a cosine, which means we say cosine theta equals adjacent, which is the A side for this label, over hypotenuse, again, the square root of a squared plus u squared. So those labeling conventions, they're necessary. I mean, we're just using trig functions here, so, ka, toa, right? But notice the way we're labeling these to make it all work. Now, you still may be wondering, well, how do I know which model to use? Again, I think with some examples and practice, it'll become clear. For now, notice kind of the big takeaway on this one is the plus sign between the terms in the root. That only happens in the case where you have that label as the hypotenuse, that is the root expression in a triangle. Those are little tips that can help you remember what's going on with these. Okay, let's keep rolling to our last one, third model. So this time for integrals involving, thirdly, for integrals involving the square root of u squared minus a squared. Now, I know what you might be thinking. Hey, wait, didn't we already see that? No. If you look back up at the first model, there's a key difference. This one, the first one, which I will just kind of note here, this is a squared minus u squared. And notice the difference of the order for this third model. This one is u squared minus a squared. And so the order, of course, does matter when you're subtracting terms. Those are different. You can't just switch the order of the terms between subtraction. Subtraction's not commutative. So u squared minus a squared now is what's underneath our root in this third model, as opposed to a squared minus u squared in the first. That will be a distinguishing mark, as you'll see with the examples, for us to tell which model we're going to use. Now, you still have to understand, what the model is, how the triangle is labeled, so you can know how to use the model. But I'm just pointing out these little tips to help hopefully distinguish and memorize them. Now, for ratio involving u and a, we've been doing this every time. Notice ratio involving u and a, ratio involving u and a. This has been a theme. You'll see why with the examples. But ratio involving u and a, again, how this is labeled matters. So we have theta in the bottom left corner, as usual. We have the right angle in the bottom right corner. We have, this time, we have our vertical side on the right of our triangle labeled as the square root of u squared minus a squared. We have the horizontal bottom side labeled as just a. And this time the hypotenuse is labeled as u. And this is all in relation to theta, which means we would call the bottom side labeled a the adjacent side in relation to where theta is. We would call the root, in this case the vertical side across from it, would be the opposite side, again labeled in relation to where theta is. And then, of course, the hypotenuse is always the hypotenuse. It's the slanted side across from the right angle, and that in this case will be where u is. Now, that matters because if you're trying to find a ratio involving u and a, well, notice where those are. That would be the adjacent and the hypotenuse. So we only have an option for that known as cosine theta. So again, if theta is our angle labeled in the bottom left corner, then cosine of that angle is equal to the adjacent, in this case a, which I'll label here again in our little ratio. A is the adjacent side, over the hypotenuse for ka. So ka toa, adjacent over hypotenuse. In this case, the hypotenuse is u. So cosine theta equals a over u. And again, the goal right now is to make sure that this seems believable. It's going to take some practice to make it familiar and usable and easy enough to memorize and recall when needed. Or, moving on here, so a ratio involving the square root of a squared plus u squared. Nope, that's a typo. That's supposed to be a minus. Sorry, let me rewrite that here. This is supposed to be the square root of a squared, square root of u squared minus a squared. And a, if we're trying to use the square root of u squared minus a squared, which is the one we're in, that's the case we're in. I just misprinted that bottom line, sorry. There it is, fixed. And a, then of course, we've already labeled that root is the opposite. That is, the square root of u squared minus a squared is across from theta, so that's the opposite. And then, of course, to find a is the adjacent. So to put those together, we would have tangent theta, which is the trig function that ties together the opposite and the adjacent. So that would be the opposite side, which is our square root of u squared minus a squared over the adjacent side, which is our a. Okay, so there we go. We have all these trig ratios now being used in the context of these right triangle models. You may say, well, that seems a little complicated. Do we need all this stuff? Really, I think this is the best way to go about it. So yes, it will take some practice, but being familiar enough with all of these triangle models to not only know where they are, and again, notice the differences, like which one has the plus sign, as I mentioned in Model 2. Notice the difference in the order of terms for Models 1 and 3. If u is some function of x, as we've already defined it, then you will find that for the first model, when you have a squared minus u squared, a is a constant, you'll have just a number as the first term inside the root. and you'll have whatever function of x as the second term, right? That order helps you distinguish model 1 from model 3, which would be the opposite. It's the square root of u squared minus a squared. So there will be some function of x as the first term, and then just some constant number for the second. Those little details will help you memorize these and hopefully find them usable as we try some examples with them, which we will do next. All right, let's try an example here. Our first one, where we want to evaluate the integral, begins as follows. We have an indefinite integral of a fraction whose numerator is x cubed and whose denominator is the square root of 1 minus x squared, and this is all dx. Now, what you'll want to be in the habit of doing is identifying immediately what you're working with. Remember, if you have a whole bunch of calculus experience at this point, or it's building at least, you could say, and you already know stuff like substitutions, use substitutions, you may be tempted to use some of those things you already know, and that's fine. What you'll find is that some of those things don't always work, and that's the case here. If you tried to do a basic U sub on this one, it really wouldn't go anywhere. You can try it, that's the problem though. You're going to hit a dead end and think, I wish I had another tool to use. Well, we now do, and so we're going to practice using that. I want to identify maybe a good first step in this, which is to notice that you have this root in the denominator of our given integrand. That was specifically, I'm gonna kind of highlight this and just bring it over to the side. So when you're dealing with an expression that involves the square root of 1 minus x squared, this is going to help identify which model might make sense here. And sometimes, to be quite honest, some of the details don't come together until you just start trying stuff. So don't be afraid to just kind of start working on it. And these examples should hopefully give you some confidence to work with what you're looking at in any problem like these. But here's what I mean. If you can recognize that in this denominator we have 1 minus x squared, we want to recognize that as being like, if you look up at our models, this is kind of like the square root of a squared minus u squared. Now, can you think of why I would have picked out that model? Again, let's go back up to our options. We only have 3 to pick from here. Why would I have picked on a squared minus u squared underneath the square root? Well, obviously, 2 of them have minus and 1 has a plus. Well, in this example, it's certainly not a plus, so we can ignore model number 2. It could be model 1 or 3. How do you know which one it is? Well, again, it's where the constant and the function of x are set up. In the first model, as we said, you have the constant term first as a squared minus u squared. And in the third model, you have the constant term second, u squared minus a squared. And by constant, I mean, in the case of this example, just the number 1. So I'm calling that a squared to be representing the constant of 1, which tells me, this is the a squared minus u squared model. Okay, clear enough? So one key step, once you identify which model you're working with, any of these problems, is to draw the right triangle for the model. Now I'm going to do this really in 2 ways. I'm going to draw, if you look back way above where we had our right triangles, I'm going to do the same orientation where the right angle is in the bottom right corner. The bottom left corner I'll label as theta. And then, depending on which model you're using, you will label your sides accordingly. In this case, when you have a squared minus u squared, again, notice the order of those letters. The constant term is first, and then the expression involving x, which in fact, let's be clear. So a squared for this particular problem is 1, and u squared is x squared. That tells us what a and x are, actually. So we want to note that. Now, if you're kind of just, again, getting used to the models above, you may be looking at them and just using the u and the a, and that's okay. In this case, since we have the constant term first, a squared minus u squared, we're actually in model number 1. Let's take note of that and then try to draw it accordingly. So let me note here, we are in, this is model number 1 above, and I'm going to highlight that just so we can keep that in mind. That's important to recognize. Once you know which model you're using, of course, you just have to draw it accordingly. If you're in model number 1, a squared minus u squared, notice in that triangle model you have the root in the bottom, at the bottom horizontal leg, you have A as the hypotenuse and you have U as the opposite side. So we want to label our triangle accordingly. So let's do that. I have the root in the horizontal bottom leg, so that's square root of A squared minus U squared. I'm going to leave that in its symbolic A and U form first. We'll replace those with what they're equal to soon here next. So the bottom leg, square root of A squared minus U squared. The vertical leg is U, the hypotenuse is A. So vertical leg is U, hypotenuse is A. We have those labeled accordingly. Now, it's also helpful to replace U and A with what they're equal, as we've already identified from just matching up what's in this problem. So we're going to do a second picture, and I think this is worth the time and effort. It's not that bad. We're just going to redraw our right triangle, but instead of using U and A, this time we're going to use 1 and X, just like we have in this problem. So since we matched up A, if A squared is 1, that must mean then that A equals 1, which means I'm going to put 1 as the hypotenuse in this diagram. And if U squared is lining up with X squared, that must mean that U equals X. So that means on the vertical right side leg, I'm going to put an X instead of a U. And then we're going to put our root expression involving, in this case, instead of A squared minus U squared underneath it, we're going to put 1 minus X squared using the actual variables or values from this particular problem. Okay, so we've now converted the general model to the more specific occurrence of it in this problem using simply what A and U represent by matching up the model. Let's not forget theta is in our bottom left corner. Once you have the triangles drawn, and I know it seems like a bit of work at this point, but again, if you recognize the correct model and simply translate it all over to the variables you're using, this is most of the work here, because the rest is hopefully some pretty familiar trig. Let's now get our trig ratios, and you should have 2 of them. The first is involving U and A. Or I don't know if I use that as the first one. Yeah, U and A is the first one, as I've just listed them in the order right of that I did originally. The first ratio I said was U and A. We'll get one for that. And then the second one, as I've said, involves the root, which changes every time, and A. So I'm going to write it that way: the root and A, because the root, it varies a little bit in each model. So let's see if we can now put these 2 ratios at least down. What can I use involving U and A? Well, look at our model. U is the opposite side of where angle theta is, and A is the hypotenuse. So I'm going to label those in just our general model picture. Of course, that translates to the one we've replaced with our values. So our hypotenuse, which was 1, and our opposite, which was just X, those are still where they are. Of course, adjacent would be the bottom side. And so what trig ratio can we make that uses U and A? Well, by U, we mean the opposite side in that original diagram. So that's just X. And then A, of course, is the hypotenuse. What trig ratio uses opposite and hypotenuse? That's the question. There's only one. It's sine. So we can say sine theta equals opposite, which is, I'm going to use our new values that we've now had in this problem. Opposite is X, and then over hypotenuse, which is now 1 for us, as labeled. And then we can get our second ratio similarly. We want to use the root expression and A. Well, notice where those are. The root expression is in the adjacent side, and A, which is now replaced as 1, is the hypotenuse. So which trig function uses adjacent and hypotenuse? Well, cosine. So we'll say cosine theta equals adjacent, which is the square root of 1 minus x squared, over hypotenuse, which is just 1. Okay, so these are really important, what we've now used or created with these trig ratios. I'm just going to kind of star those to note that. There's more to do with them, but it's important to have them at all. So we're going to just kind of pause there and note that we do. We have those trig ratios. That's always a main step. Something we should note as well, and this matters, again, usually textbooks will refer to this in detail, which you may have already read or hopefully read. I want to just reference it here. So with this first ratio, we ended up with sine theta equals x over 1, which really just means sine theta equals x. We also have to just make sure that the domain restrictions make sense. These have to be one-to-one functions if we're going to do such a substitution, and we can verify that with the following. So notice that the domains, let's see, I'll put it this way. Domain of the square root of 1 minus x squared, which was our original root term, this is just a little algebra question. What's the domain of the square root of 1 minus x squared? Well, x would have to be between -1 and +1. However, since this root expression is in a denominator, it couldn't even be equal to. So it has to be greater than -1, but less than 1. Equal to is generally okay for the root, but you can't divide by 0, so that wouldn't work. So we know that the domain of this expression, really it's 1 over the square root of 1 minus x squared, is strictly from -1 to +1 for x. But then also, the domain of sine theta would be such that it's between less than or equal to, greater than or equal to, or less than or equal to -1 to +1. So sine theta, we know this from trig, sine theta is between -1 and +1, right? Well, notice these have to match, but we have to use the more restrictive one. So since x has to be strictly between -1 and +1, then we're going to have to say that sine theta has to be strictly between -1 and +1. What does that mean for theta is the question, right? Well, think of our unit circle. Where is sine -1? At the bottom of it. Where is sine +1? At the top of it. If sine has to be between those, we're talking about quadrants 1 or 4, but specifically if it's a strict inequality, then it has to be less than or equal to. We can't actually get there. So we'll say this, that from -π/2, strictly theta has to be greater than that, but less than +π/2 in order to maintain all of these restrictions. So in summary with that, as long as theta is restricted to be between -π/2 and +π/2 strictly, that is quadrants 1 or 4, then we have one-to-one functions, which means this substitution is valid. We had to double check that, and that little side show is just to make sure that that is true. So let's now continue on and actually try to do a substitution. So I'll say here now, try substitution. We've been setting up all this work for what, right? Well, if you take the original integrand, which was given as the fraction whose numerator is x cubed, whose denominator is the square root of 1 minus x squared, this is all dx, and we know that no other integration tool we have will get through this one. Maybe the whole goal of this trig sub process, this topic, is to say maybe we can replace everything in this integrand with some form of trig function that's easier to work with. That's literally all we're doing. We're just replacing this integrand with some kind of trigonometry. Now, some of that may already start to be evident, and some of it maybe not quite yet. In order to replace 1 minus x squared, that's not looking too difficult because notice that's exactly what cosine of theta represents. So that's looking good. We can replace that with a cosine. The question is though, what about this x cubed and this dx? I don't even have a dx in the picture yet, right? So we have to do a little bit of work there to get this prepped. So since I'm going to say here, recall what we've already set up, which is that x equals sine theta. That was that first ratio we ended up with, x equals sine theta. And if that's the case, and I take the derivative with respect to theta of both sides, so I'll say d theta of x on the left side equals d theta, the derivative with respect to theta of the right side, which was a sine theta. Then the following happens. We end up with dx over d theta on the left side equals derivative with respect to theta of sine theta is just the derivative of sine, which is cosine theta. And then, of course, if you just multiply by d theta on both sides, we end up with dx equals cosine theta d theta. Well, this is looking good because now it looks like we have something we can substitute. I'm going to get a color out here to highlight this. Hopefully one I haven't used yet. Let's see. Kind of hard to identify. Let's see. So now what we can say is that dx, in our original integrand, is now replaceable with cosine theta d theta. Those are simply equal. So doable. Furthermore, as we already noted, let me highlight this as well, the square root of 1 minus x squared, which was our original denominator, that's replaceable with, well, just cosine theta because of the way those ended up equal in our ratio. And then furthermore, we have this x cubed to deal with in the numerator. But we already know that sine theta is equal to x, which means that will replace that piece. So actually, everything is all primed for a substitution to get out of this confusing original form and into a more user-friendly trig form using a trig sub. Now, there's a lot of work to set this up, obviously, so it takes a lot of practice with these. But once you get the hang of them, I think you'll find that there's a lot of value in this method. So let's do this now, just all the replacing. The rest is easy. In the numerator, instead of x cubed, we're going to replace x with sine, which means this is really just sine cubed theta. And I'll even highlight that in the same way that we've been using for the colors here. Let's see. Instead of dx, which was at the end of our original integrand, we're going to replace that with cosine theta d theta. And yes, I'll even highlight that in the same color as used. Can help us stay on track here. And then with our denominator being, used to be the square root of 1 minus x squared, well, we just found out earlier that that's really just cosine theta. And yes, let me highlight that in the same color as well. So everything's getting replaced by something that came about from this right triangle trig model. Now, that doesn't mean we're done. I mean, all we have is a bunch of trig in this integral. Now, maybe that's easy, maybe not. You'll notice something tempting in this one. I just want to point it out. We have now currently, we've converted over using a bunch of trig sub to an integral of the fraction whose numerator is sine cubed theta, and then we have a denominator under it of cosine theta, and that fraction is being multiplied next to it, after it, by cosine theta d theta. It's tempting to say, oh look, cosine thetas will cancel. There's one up top, there's one below. Well, okay, that's true, but if you cancel those cosine thetas, you're kind of stuck because all you have left is sine cubed theta d theta, and there's no good way to integrate that. So unfortunately, it's still possible to get stuck even after all this work has been done. So I want to go through another way to get around this. There might actually be a couple ways to substitute your way through on something like this. I'm just going to pick a way, and hopefully you can follow it. If you see another way somewhere else that's possible, then it might also work. But let's do the following. I'm going to take this integral and rewrite it again. Instead of the sine cubed theta, I'm going to split that up to be sine squared theta times sine theta, which of course is equivalent to sine cubed. And then I'm going to keep that all over the cosine theta that was underneath it, and then keep it multiplied by cosine theta d theta, all of that which we had in the previous step, but it's a little bit more convenient to use at this point. If we do just one little trig identity substitution here, we're going to rewrite this integral, and I'm going to replace that sine squared theta that we had in the numerator with its equivalent of 1 minus cosine squared theta. So that's just getting replaced. We still have after it a sine theta. We still have under it a cosine theta. And then all of that is still multiplied after all of it by cosine theta d theta, which hopefully all matches up from one step to the next here. Now, why would we do this? Well, notice here that replacing the sine squared theta with 1 minus cosine squared theta kind of fixes one of the problems we had at the previous step. Remember how we said we really shouldn't cancel those cosines, because if you do, you're left with something that's not doable, just a sine cubed theta d theta? Well, now actually if you cancel the cosines, it works out just fine. I know that almost seems unfair that it would be some simple step that makes it doable. But now watch, if you cancel these cosines, thetas, a top, one on top, one on bottom, what are we left with? Well, something we can do a substitution with. We now have the integral of, in parentheses, 1 minus cosine squared theta, close parentheses, and then times sine theta d theta. Well, this is set up for typically a u substitution. I'm not going to use the letter u because we've already kind of overused it above, and that's a little bit dangerous. So I'm going to use, I'll pick on w, I guess. Just got to use something different. And I also try to use a different color, which is hard to do. I'm trying to use reasonable tools here. Let's try the following. If I use some kind of scarlet color, and we let, instead of using a u, I'm going to use a w. What kind of substitution would you do in an integral like this? Think back to what you know about substitution, right? It would help to let w equal cosine theta. Why? Because then if you took the derivative, you'd have, with respect to theta, you'd have dw d theta equals, the derivative of cosine theta would be negative sine theta. And then if you multiply by by d theta, on both sides, you end up with dw equals negative sine theta d theta. Why do we care? Because that's, a huge portion of this integral we're trying to substitute. So we're ready to go. Let's go ahead and transition on to a next step. After using this substitution, we now really just have 1 minus w squared in parentheses instead of the 1 minus cosine theta squared. And then after it, we have, instead of sine theta d theta, we know we're off by a negative sign, but we can easily fix that. So I can throw a negative sign out in front of our integral in this last step I'm on here, and then use a sine, just a dw was replacing negative sine theta. So if I put the negative in front of the integral, take care of that negative sign, and then let dw replace sine theta d theta, then we end up where we are here, which is we want it negative integral of the quantity 1 minus w squared in parentheses dw. All right, so slow that down, back it up, try it again, or watch it again if it's not clicking. Hopefully that's making enough sense. But we're not done because nobody cares about w or u. We want to get back to the original problem. No one even cares about theta here. If you go back to the original, it was only x that was in place. So we have a lot of back substituting to do, not to mention we haven't even done the integral yet. So let's finish this last step with the following. These are now simple antiderivatives. This is going to be negative, and then with respect to w now, this is going to be an antiderivative of w minus w cubed over 3. Just doing my antiderivative rules there. Put that in brackets because of the negative sign that's out in front of it. Be careful with that. And then don't forget your plus c. This is an indefinite integral, so we have to put our constant there. But then let's replace w with what it was equal to. What was w equal to? Go way back at the ranch. W was equal to cosine, right over here, cosine theta. So that means we have negative, in parentheses, cosine theta minus cosine cubed theta over 3. That's all in brackets. And then plus c. But then what's crazy is nobody even cares about theta, so we have to replace yet one more time. Don't worry, it's not too bad. We know already that cosine theta equals something, or we could find it simply by our triangle model. So go way back up. Remember our models? Well, we're going to use them again. So go back to the one we replaced. u and a with as second ones, most relevant to use. And we want to find what cosine theta is directly from that model, knowing that cosine is adjacent over hypotenuse, right? The way they are labeled, adjacent is the square root of 1 minus x squared. Hypotenuse is 1. We're simply going to use those to create or replace now, instead of cosine theta, we're going to use the ratio that we get from that. So we'll say instead of negative cosine theta, we're going to have negative, and then we're going to have the square root of 1 minus x squared. Again, that's adjacent over hypotenuse, knowing that adjacent was that expression and hypotenuse was 1. So that's what cosine theta is. And then moving on, we'll say minus. The next term, well, we already know now that cosine theta is that. So we'll say minus that same root, square root of 1 minus x squared. But now it's cubed because we're replacing cosine cubed theta. And then we have to put that all over 3 because it was over 3. And then a plus c. And after all of that work, we should finally be done with a solution to that original integral. Let me just add a note so it's not confusing. The cosine theta turns into that root. I'm just going to say c model above. As I scrolled up there, I just want to make sure it's written there as well. In both of these cases, we're replacing cosine theta with the square root of 1 minus x squared. Our second example is the integral of a fraction whose numerator is the square root of the quantity x squared minus 1. And then under that, in the denominator, is an x to the fourth. And then, of course, this is all dx. All right, so our first step, as we've already kind of seen, is to understand which model we may be working with. Now, you look at the root portion of the integrand, which for this one, of course, is the square root of x squared minus 1. And that helps determine which model to use. Again, refer to the list above in our notes. If you're using that case, notice there's a function of x as the first term under the root, and then a constant as the second term, and there's a minus sign between them. Those are some clues that will help line up, which model we're using. So if we look at our list, you'll notice one of the models that seems relevant is where you have a right triangle with the right vertical side of our triangle being the square root of u squared minus a squared. And that also has a bottom leg of a and a hypotenuse of u. So again, we're just kind of matching this up to the model that we see above. But of course, we want to also refer to it in the context of these particular values. So instead of u, we want to know what u is, right? Or instead of a, what is a? So we're going to now translate that as well, like we did before, to a more meaningful triangle that includes the values of this problem. Of course, we have theta in the corner. I should put that in there in the model as well. Bottom left corner is where I'm putting theta, just to kind of stay consistent with that. But then if you start plugging in what this actual problem has, instead of a, of course, a squared is what you're seeing in the model, but our problem has a 1. Well, then 1 squared would mean that a is 1. So we'll put a 1 in the bottom leg of our triangle to represent where a would be. And then the hypotenuse, of course, is, in this case, it's u. Well, our model is supposed to be u squared. And in this problem, that was x squared, which means typically that u, or simply that u equals x. So instead of a u in our hypotenuse, I'm going to put an x there. And then, of course, on the vertical leg, we're going to put the root expression, but not in its u and a form, in its actual form of this problem, which is the square root of x squared minus 1. That was our numerator, and that expression is what helped us choose which model we're using. All right, so hopefully this is all lining up, right? We're using the general model as selected from our notes above, and then we're writing out also I'm doing this in diagram form, we're writing out the particular form of that model that uses the u and a values from this problem. Now, once we have that set, and hopefully, again, those models will become familiar as you practice with them, we want to do our ratios. and typically there are two of these. So we'll just do them as we've already stated above. So first, we need a ratio involving u and a. And in that case, again, you're looking at your triangle, and we're going to work with the one we've written that's kind of in the language of this problem. So I'm using the x and the 1 instead of the u and the a. So in that case, which trig ratio would involve u and a? Well, u in the model is the hypotenuse, and a is the bottom leg, the horizontal leg. So in this problem, that would be a hypotenuse of x and a bottom leg of 1. Well, which trig function uses those sides? Obviously, the hypotenuse is the hypotenuse, but the bottom side, the horizontal side in this problem, related to where theta is, would be the adjacent side. And so which trig function uses adjacent and hypotenuse? Well, cosine. So we're going to say the ratio that involves u and a would be now cosine theta, which is equal to adjacent, which is 1. That's our adjacent side for this problem's model. And then over the hypotenuse, which is an x. So we have cosine theta equals 1 over x as our first ratio. We'll do more with that in a bit, but I want to put our second ratio down because, again, as we say above in our notes, I'm just kind of doing what we've already stated while above, so review those model notes as needed. But the second ratio we want is the one that involves the root and a. So we want u and a, and we want the root and a. So let's kind of go to our model and see the root. Notice that would be on the opposite side, the side that's across from theta. That's where the root is in the model. So we want that side opposite, and then a, of course, is still on the adjacent side next to our angle theta. So which trig function will involve the opposite where the root is and the adjacent where the constant is? Well, that would be tangent. So we'll say tangent theta equals opposite, which is our square root of x squared minus 1, over adjacent, which is 1. And we're just, again, pulling those side labels from the model that is matched up to this problem as we've already drawn. Okay, so those are all important. We have to have those ratios to do any sort of substitution. Now, it may or may not be clear yet how that's going to go. So let's do a little bit more work to see if we can eventually turn our original integrand into, with some substitutions, trig functions that we've now kind of brought into the picture. Of course, we've only brought in cosine theta and tangent theta so far. Now, I want to point out one other thing, too, and that is you'll find that this first ratio we had, the cosine theta equals 1 over x, it's more useful to write that using where x is not in a denominator here. So we're going to do a little bit of a flip here. If I were to flip 1 over x, of course, that would turn into just x, but then I'd have to flip the other side as well, which is algebraically acceptable. You can flip both sides of a proportion in that way. So if you flip cosine upside down, that's 1 over cosine. Well, guess what? That is really just secant theta. So if you flip cosine to be secant, which is 1 over cosine, but then you also flip the other side, which was 1 over x, now to be just x over 1, or just x, that's a valid algebraic maneuver, and it helps to simplify what we have. Furthermore, it puts x in the picture. You know what, just to make this a little bit more visually familiar, I'm going to switch the order of this. Instead of secant theta equals x, I'm going to write it as x equals secant theta. Obviously, the same thing, just flipped around, switching the sides of the equation. Why? Because it just looks a little more familiar. Now, I want to be able to get the derivatives in play here. I know I need to end up with a dx. We have an x. So let's take the derivative of both sides with respect to theta. And I'm going to put this in, I guess, throw this in a different color. If I want d over d theta, the derivative with respect to theta of both sides of this equation that we've now been working with, that we got from our ratio involving u and a, if I take the derivative with respect to theta of both sides of this, we'll end up with, on the left side, now that I've flipped those, dx over d theta equals, on the right side, I want the derivative with respect to theta of secant theta. Well, those variables match. They're talking the same language. That's just the derivative of secant, which happens to be secant tangent. So I want secant theta, tangent theta. And then in order to get dx in the picture, which is my motivation right now, so I can replace the original dx with something, I'm going to multiply both sides by d theta. So if we do that on both sides, we'll end up with really just dx equals secant theta tangent theta d theta. Now, this is a substitution that is something we want because dx will be able to replace the original dx in our problem. And obviously there's more to replace, but that's one motivation to be doing what we just did. We need to be able to replace or substitute the original dx. This is also the step, as we saw in the previous example, where we need to, when doing a substitution, check to make sure both functions are one-to-one. So what we're going to do here is, we'll just note this, we're going to check one-to-one, and that is for, in this case, x and theta. It involves the substitution that we just did. So what matters here? Well, if you take a look at these two functions, we have cosine theta, but now that's been turned into a secant theta. We have this 1 over x, which means it involves x. If you go back to the original function, the x in the numerator was in this root, inside this root, that is square root of x squared minus 1. So specifically, we need, of course, the root that's in our numerator to have something positive or 0 underneath it. That means we have to have x squared minus 1. That's the expression within the square root that's in the numerator here. That expression has to be greater than or equal to 0. Okay, in order for the domain of that original function to remain intact. Well, if that's the case, then if I add 1 to both sides, this means x squared has to be greater than or equal to 1. And that means that the absolute value of x has to be greater than or equal to 1. But if x equals the secant theta, as we've already done in our ratio with our substitution as we've seen, then really if I replace x with secant theta, that really means the absolute value of secant theta needs to be greater than or equal to 1. And that means that, of course, theta must be greater than or equal to 0, but less than pi over 2, or theta has to be greater than or equal to pi, but less than 3 pi over 2. Now, if that's very unfamiliar, I recommend reviewing some trigonometry. In fact, I'm going to just say that. See trigonometry, and specifically look at the inverse secant function definition. You have to restrict the function in order to make sure it's one-to-one, so that it has an inverse. That's all part of trigonometry. Review that as needed. That's exactly where these restrictions come from. And it's also related, of course, to the value of secant and its graph. If the absolute value of secant has to be greater than or equal to 1, then of course the secant values need to be bigger than -1 or less, bigger than 1 or less than -1. And that all goes back to you can see that in the graph of secant. That's kind of just something you might want to review in trigonometry to make sure you're confident with that. What does that mean? Well, that means we have a restriction on theta because of our substitution. We have to make sure that this all still remains. We've turned x's into thetas, but the domains of all the x expressions need to hold true. So to make sure that's all the case, theta does need to be restricted now that we've identified where. That's what we can say about that. So just something to note for now. All right, I think we're ready to do some substitutions to make this thing start looking pretty. So let's take our original problem. I'm just going to copy it down again. It's the integral of a fraction whose numerator was the square root of x squared minus 1. The denominator was x to the 4th, and this is all dx. And we're going to start doing some replacements because we now know a lot. In fact, and I'll highlight this to hopefully make it followable. If you take the numerator, which is the square root of x squared minus 1, you'll notice that that actually equals tangent theta with this substitution. We said previously from one of our ratios that tan theta equals that very square root of x squared minus 1 all over 1, namely just that root. So that'll get it easily replaced. If you look beneath in the denominator of this original problem, you of course will find something else that needs to be replaced, and that is the x to the fourth. Well, if x is equal to secant theta, which we got from our first ratio, then we can replace x with secant theta. And of course, we got the secant because we flipped that original ratio upside down. You can recall that to make sure that's clear. But all we want to do now is start making these substitutions. So I'm going to rewrite the integral. And in the numerator, instead of that root, we're just going to write tangent theta, because after all, that's what it equals. And then in the denominator, instead of writing x to the fourth, since x is really secant theta, we're just going to call that secant to the fourth theta. And then, lastly, of course, let's not forget all the work we did with, what was another color I could use here? How about this? So dx, nope. Let's get a highlighter out here. Dx which also would need to be replaced. We did the work to find out that dx really equals secant theta tangent theta d theta. Again, all these substitutions are now coming into play. So if you haven't already kind of picked this up, in a problem like this, there's a lot of, you may say, preparation work, and then all of a sudden everything just kind of comes together. There's a whole bunch of little details we've been putting kind of on a little sideshow, but now we're putting it all back in to make this work. So I'm going to replace dx with secant theta tangent theta d theta, which is exactly what dx is, as we've already discovered. All right, so it gives us an integral that we can work with that doesn't look necessarily simple, but at least it has some possibilities to simplify and then use some basic trigonometric integration with it. So let's just do a little bit of basic simplification. I'm going to take what we had and rewrite it as the integral of. Now we'll write it this way. Notice in the numerator you have tangent theta and then another tangent theta down the line. If you were to multiply those together, of course, then you'd get tangent squared theta. So we're going to write it that way, a little bit more simplified. Tangent squared theta over. And then notice we had a secant to the fourth theta in our denominator, but then next to it was just a secant theta in the numerator. So if we reduce those, then that really means we have three of them in the denominator. So I'm going to say that underneath the tangent squared theta, we have this secant cubed theta. And then, of course, just a d theta after that. That just kind of blends all this trig together, doing some very basic kind of just fractional simplification. All right, so at this point, you may still be wondering where we're going, right? We've turned everything we had originally, which didn't have a good way to integrate. We've turned it all into trigonometric expressions, but are those doable, right? Because that's the whole point, is that they should be. And the way it's currently standing with a tangent squared theta over a secant cubed theta, d theta, nothing is quite ripe enough to proceed. So let's do a little bit more work on this. And specifically, let's use some familiar sine and cosine language. So I'm going to rewrite this integral yet again. Tangent squared theta that we had in our numerator, we're going to rewrite that as sine squared theta over cosine squared theta, because actually that's what it is, right? Tangent and sine squared. So tangent is sine squared. Tangent is sine over cosine. So tangent squared is sine squared over cosine squared theta. That's covering the tangent in our numerator. But then if I was dividing by secant cubed, let's remember secant is 1 over cosine, which means if I'm dividing by secant, that's the same thing as multiplying by cosine. So we're going to put a cosine cubed theta in the numerator to cover that secant cubed theta that was down below it, just kind of flipping it upside down and moving it over. And then, of course, don't forget to finish with d theta. Okay, it's getting better. Notice some more stuff we could do. These cosines will reduce. So let's take care of that, making this, of course, the integral of sine squared theta, which we just had in our first numerator there, times, if I cancel the two bottom cosines with two of them that are currently on top and those cubes of them that we have there, that would leave an extra cosine on top. So really we have sine squared theta times cosine theta d theta for the full integrand. And at this point, maybe by now, you might start to recognize something like this. This can be done, where we are now, can be done with a substitution. Now, this would be traditionally called maybe a U sub, but we've already kind of used the letter U, again, with these models for this trig sub. But so I'm going to use something different. I'm going to use W. We'll say let's let W, I've done this before when U's already taken, but let's let W, and in this case, we want to let W equal sine theta, which if you're familiar with the U subs of basic integration, that would make sense. Let's see why. If I now take the derivative of this with respect to theta, then I will say that dw is equal to cosine theta d theta. So I'm doing derivative with respect to with respect to theta of both sides, giving us then dw equals cosine theta d theta. Why is that helpful? Well, because that's part of what we have in this current form of our integrand that we would love to be able to replace. And furthermore, we can then use the substitution for w to replace the sine that we have also with it. So it's actually a helpful material that we can use to go forward even more. Let's do that. This becomes the integral of, instead of sine squared, again, knowing that we've now used w for sine theta, we'll call that w squared. And then cosine theta d theta is all going to get replaced, as we've seen, with dw. So with just some kind of smoke and mirrors substitution, which is really a lot of what we're doing lately with all this trig sub and even the more basic sub, we can now get a very familiar integral out of this. The antiderivative of w squared would be w cubed over 3, and then of course plus c, since this is an indefinite integral. But remember, when you're doing substitutions, nobody really cares about the substitutionary variables. So we have to go back actually a couple steps. Most immediately, w is equal to sine theta. So if we go back and replace that, our current result will be sine cubed theta instead of w cubed. And that's all over 3 still. So sine cubed theta over 3 plus c is where we are so far. But really, we don't even want sine theta in our answer. Remember, the original problem was given in terms of x, and we kind of masked that over with a whole bunch of other substitutions. We have to get back to our x here. Kind of a funny saying there, but that's the way we want to finish. If that's where we started with the x, we have to finish with that. So let's do that using our model. In fact, let me put this off to the side. So using our model, and by my model I mean the triangle model we have already been using. We drew it above. We drew it above. I'll put it here again. It's the one in particular form for this problem, which had an x in the hypotenuse, a 1 in the bottom, and then our root expression on the side. So let's redraw that to make sure we're familiar with that. X in the hypotenuse, 1 at the bottom, square root of x squared minus 1 on the side. Again, just pulling that directly from above. I kind of redrew it. You don't have to if you're working just on your own paper there. But that's what we want to use, and of course theta is in there, and that's part of the point. We have theta in the bottom left corner, and if that's the case, we can use really any of our known trig ratios with the right triangle. So I could now find out what sine theta is in terms of x. Sine theta is opposite over hypotenuse. Well, opposite is our root expression, square root of x squared minus 1, and then hypotenuse, of course, is x. So sine theta is equal to square root of x squared minus 1 all over x, and that's how we can replace the sine theta that's in our current answer, so we can finish with something in terms of x. So let's do that, and our final result will say that we have in our numerator, instead of sine cubed x, it's really the square root of x squared minus 1 over x. That's replacing sine theta, but that's cubed, and then that's all over 3 plus c. And then that's maybe not quite the simplest way to leave it, so we could go a little bit further. Maybe I'll just leave it this way. How about we'll pull the 1/3 out front, times, we have a fraction then whose numerator would be x squared minus 1 to the 3/2 power, right? There already was a square root, which is a 1/2, but you're multiplying by 3 for the new exponent there that came with the substitution for cubing it. So x squared minus 1 all to the 3/2 power, all over then x to the 3rd as well. You'd cube that denominator of that substitution also, and then plus c. And I think that's probably a good place to finish for now. All right, our third example is the following. We have the definite integral this time. So definite integral from 0 to a as our bound, lower bound 0, higher bound a, upper bound a. And then the integral, the integrand is a fraction whose numerator is given as just dx, which I know normally is at the end. We'll explain that in a second. It's the same thing as being up there, but times 1. And then the denominator under that dx is a set of parentheses containing a squared plus x squared, and then those parentheses, which close there, are to the power of 3/2. And then we have this extra condition provided in the problem that a is greater than 0. Okay, and that's where we're starting. Now, if we're in the context of these trig sub problems, and we're familiar or getting familiar maybe with the models that we have above to pick from, you may start to think, well, wait a minute, this one doesn't really look like any of those models because I don't see any root expressions, which is kind of where we start to identify which model to use. So I'd like to suggest that that is true at first glance, but if we do some basic rewriting, which is really just some algebraic rewriting, it will start to look familiar. So I'm going to rewrite this originally given problem as now the integral from 0 to a, with those being our bounds, of a fraction whose numerator I'm going to just put as 1, and I'm going to put the dx at the end, which is technically the same thing as we were given. You're multiplying the dx times the 1 up top, which is where it was showing up originally. But just so it makes sure it looks familiar, I'm going to write the dx at the end. And then instead of writing the denominator as it was given, I'm going to recognize something here, that the power of the fraction, the power of the quantity in parentheses, which was a squared plus x squared, that quantity was raised to the power of 3/2. Well, as we know from algebra, a half power is really just a root in disguise. So we're going to rewrite that as the square root, which is what a 1/2 power would do, the square root of a squared plus x squared, which is exactly what was in the parentheses. But then we can't ignore the numerator of that power that was a fraction, that being a 3. So we're going to put a third a power of 3 outside parentheses containing this square root. So I'm rewriting this so that you can tell, oh, actually there really is a root in this expression. Furthermore, if you go up to our models that we have to pick from, only one of them has a plus sign, a sum between the terms that are in the root, which means we should be able to jump directly into our model triangles. I'm going to draw that out now that we have above. And also it's convenient in this problem that they're simply using x and a. We don't have to worry about any crazy rewriting or substitutions there to get it to be matched up with our problem if you're just using the general model. So what I mean is, if you compare the ones we have above, okay, so we have our right triangle with our right angle in the bottom right corner, theta in the bottom left corner, and then we know that there's a model that matches the sum in the root, and that would be the one on the hypotenuse. So on our hypotenuse, we're going to put the square root of, now the way we have it written in this problem is a squared plus x squared. Of course, addition is commutative, so you could technically write the x squared plus a squared in that other order. That's fine as well. It's equivalent. The vertical leg on the right side of our triangle model would be an x, and the bottom horizontal leg would be the a. Again, just matching with what's provided and with the models that we have above. Now, that's to get us oriented and started. Let's also recall then that across from theta, we have the opposite side where the x is. Next to theta, we have the adjacent side where the a is. And then, of course, the hypotenuse, easily recognizable across from the right angle. That's where our root expression is. And that's all we'll need in this model to get our ratios going to start working on a trig substitution. Again, in every case here, sometimes I've mentioned it, maybe sometimes I haven't, the whole point of doing a trig sub is that nothing else really works very easily, right? Obviously, if there was an easier way to do this, we would do it. If in some cases you want to double check to make sure that like a basic substitution, like a basic u sub isn't available to use. In this case, it's not, because there's no part of this original integrand whose derivative is also part of the integrand. So, right, so we're kind of cornered into this method, but we're practicing it so we can get better at it. Now, at this point, let's get our ratios going. And remember, we always want to kind of expect that we'll need two of them, and I've kind of labeled them above in our little model as the first one needing to involve u and a. Now, in this problem, of course, u is designated, remember, it's u squared. In this case, it's x squared, so really u is like the x here. I'll put a little note that u equals x, just to make sure that's clear, hopefully enough from the model. I didn't draw both triangles. Sometimes I'm drawing the general one with the u and the a, and the one with the number and the x, right? In this case, I just drew the x because there was no numerical value for a. It was just given as a. All right, but in that case, u is really like the x in this case, because x squared is like u squared. Okay, so that matters because I want to write a ratio involving u and a. Well, that means I want x and a, and that would be, of course, in this case, tangent theta, because the way we have our model labeled, x is on our opposite, a is on our adjacent. So we can say tangent of a equals opposite, which is, sorry, tangent of theta equals opposite, which is x, over adjacent, which is a. And there's our first ratio that we'll be able to use. Of course, we want another one as well, because we always want to use the root if we can as well. So the one involving the root and a. Of course, the way they're labeled here in our model, the root is the hypotenuse and a is the adjacent. That would be cosine. So we'll say cosine theta equals adjacent, which is a, over hypotenuse, which is our square root of a squared plus x squared. And that'll give us yet another ratio to be using, ultimately, hopefully, for a trig sub to make this integral doable. Knowing that we're going to end up with a substitution, ideally, of course, we have to be able to replace all the elements of this integrand. So notice the dx, as we've seen already, you're going to have to be able to replace dx with something else, which means you need to get a dx in the picture from these ratios that we've now created using the trigonometry. Well, the best chance we have at that is the one that involves just the simple x, which was our first ratio, tangent theta equals x over a. The second ratio, yes, it involves an x, but it's buried deeply within the root, and that would be a nightmare to try to get that alone, so we're going to ignore that and use the simpler option, where we know already that tangent theta equals x over a. So the question is, can I first just get x by itself? And sure, of course, to multiply both sides by a, that will give us an equivalent form here of x equals a tangent theta. Again, coming directly from that first ratio that we already have. If that's the case, I can get dx in the picture by taking the derivative with respect to theta of both sides of that equation. So I'm going to do that now. You know what? I better do that in a different color, otherwise we're going to get confused. Let's see. I'm going to say this. d over d theta of the left side of our equation x. That's what I want, and I also want the same for the right side, d over d theta of the a tangent theta on the right side. What that gives us is, of course, now dx on the left side, which is good news because we need to have that in the picture so we can replace it with something. On the right side, we want the derivative with respect to theta of a tangent theta. Well, a is some constant. In fact, it's a positive constant that we said earlier. And tangent theta is something we can take the derivative of. So, of course, a constant will stay out front when taking a derivative. So I'm going to leave the a. And then the derivative of tangent is secant squared. Again, we're just using basic known derivatives. So secant squared theta, but then, of course, I'd be multiplying by a d theta on both sides because I have the d over d theta, or dx over d theta originally, but we're now just getting the dx alone by multiplying by that d theta on the both sides. So now we have dx equals a secant squared theta d theta. Okay, so we're getting there. Remember, we have to be able to replace dx and this is now getting to be a way to do that. In fact, let me highlight some things so we don't get lost. So dx at this point that we've now figured out equals a times secant squared theta d theta. Why do we care? Because we have to replace dx in our original integrand, and that will do it. But you'll also notice there's more to it. What about everything else that's in front of it, right? We had 1 over this crazy square root of a squared plus x squared, and then cubed. That was all cubed. That square root was cubed, right? So how do we replace that? Well, notice the other ratio, right? We have 2 ratios to work with here. The other one that we got from our model was that cosine theta equals a over the square root of a squared plus x squared, which is actually kind of what we want or what we need in this problem. But we'd like to replace just that expression. I'd love to be able to solve for that. So let's do some basic algebra to get that. You may recall that in proportions, which is when you have 2 fractions that are equal. In this case, we have cosine theta equals a over this root. That's a proportion. It's a valid shortcut to switch the diagonals of the proportion, meaning I can write this as the square root of a squared plus x squared. Be careful, my a's look like u's sometimes. That can cause all kinds of problems when we're using u's for other things. So we have the square root of a squared plus x squared equals a over cosine theta. All we did was switch those diagonals. That's kind of a basic move from really it's algebra. It shows up in geometry. It's just kind of an algebraic shortcut. You can do several steps algebraically to get that, like multiplying both sides by the root, dividing both sides by cosine. That's all that's happening. But that's a valid algebraic move, and the reason that helps now we can say, and we'll highlight this, that the square root of a squared plus x squared is now equal to a over cosine theta, and that is part of what we need to replace in this original integrand, that very square root. So we'll be able to do all the replacing we need at this point. We have all the tools we need. Now we just need to put it all back together. Now also, since we have a definite integral, and this is the case with these definite ones, be careful, don't forget about this, we have to consider what the new bounds might be when doing a substitution. So let's write this off to the, kind of off to the side. I want to make sure this is clear. We need to calculate our new bounds, and what I mean by bounds are the bounds of this definite integral that we started with. It was going from 0 to a, but that was when we were in terms of x. Now that we're going to switch over to theta, we're going to have to do some adjustments so those bounds are also equivalent. And the simplest way to do that is to use our first ratio. So let me bring that back into the picture here. We knew that tangent theta was equal to x over a. That just comes directly from our first ratio above. But if that's the case, then we can solve for theta. The whole point of here getting these new bounds. The new bounds have to be in terms of theta, if that's our trig subvariable. So if we take the tangent inverse of both sides, we'll get that theta equals the tangent inverse, also known as the arctan, of x over a. Now why does that matter? Because when we had a bound of 0, that's now going to turn into a new bound of whatever you get when you plug in the old one for this expression for theta. If theta is equal to tangent inverse of x over a, then 0 is going to translate into the tangent inverse of 0 over a, which is really just the tangent inverse of 0. Okay, so all these details definitely matter. And put your trig hat back on for a second, of course, or just go back and review. The tangent inverse of 0 is just 0. So actually that bound doesn't change at all. That's good news. Sometimes the bounds don't change, but we always have to double check. 0 was the lower bound. Let's see, the upper bound was what? A. Okay, well that's just a value. It's a constant represented by a letter. So we're going to translate that the same way. Instead of a, we need the tangent inverse. The tangent inverse of, instead of x over a, this is going to be a over a of course, that's just 1, no matter what a is. A is a positive constant, so we know that this is the tangent inverse of 1. Again, go back to some trigonometry. Tangent is equal to 1 at pi over 4. So the old bound of a is actually going to turn into a new bound of pi over 4. Okay, and so we'll use that for the integral when we start to reset and substitute everything in. In fact, let's go there. So I'm going to go back up and grab the original, actually the almost original. Remember how I did that one little translation to make it look like there was a root involved? I'm going to call that the one we adjusted slightly. That's the original for the practical purpose here. So I'm going to take that and bring it down to say our new integral. Now it used to go from 0 as the lower bound, but that's actually going to stay because, in fact, I think some highlighting might be helpful there. So the old bound was 0 and so is the new one, but we had to double check that just to be sure because those bounds can change. In fact, of course, the upper bound did change. So instead of the upper bound being a, now it's pi over 4. And if I could find a unique color, which may be tough to highlight those, let's use pink. So we used to have a bound of a, now it's going to be pi over 4. And sure enough, that's what we have as our upper bound. Okay, but we're in the process of putting this all together. Let's go back and recall then that original or almost original expression in the integrand was 1 over this square root of a squared plus x squared. So we're going to say 1 over the square root of a squared plus x squared, and that was all, that root was in parentheses that were cubed. And then dx. And that's what we had for our original or somewhat original integrand. We need to replace everything that has an x with now something that has a theta so we can use all these trig expressions and ideally our trig integration known methods or values. And technically, now that I've changed the bounds in what I'm drawing as the integral, I should be very careful and change everything else. You shouldn't only change half of the problem, the bounds, and not the integrand itself. So in the integrand, let's go ahead and do this. We have in the denominator the root expression, square root of a squared plus x squared. That's going to get replaced, so I'm just going to erase that. And as we know earlier, that's going to get replaced with a over cosine theta. So I'll put that exactly, a over cosine theta. And let's see, to highlight this from where it came from, let's even use the same highlighting color. So we replaced our root with that expression. But then also dx we need to replace, so let's do that as well. I'm going to erase the dx and rewrite that instead as a secant squared theta d theta. And again, that comes from something we knew earlier, which I will highlight in the same color, a secant squared theta d theta. We had already figured out that replacement for dx. All right, so let me rewrite to start simplifying this. I'm going to copy down what we have, except I'm going to let the constant factor of a that was kind of in one of our replacements, I'm going to let that float all the way to the front in front of our integral. So now we have a times the integral from 0 to pi over 4, our new bounds. And then I'm going to reduce or simplify all the trig here. Now, I'm going to not write every little detail. You may want to do that off to the side to make sure you're confident with it. Just some algebra and trig kind of combined. We should end up with, I think, secant squared theta over a cubed times secant cubed theta. And then that's all d theta. Now again, to go from one step to that next one, just to save space and time, I'm not putting every detail, but that's just some basic trigonometric algebraic movement, right? Try that out, make sure that's clear. If that's the case, then let's take this another step. Notice we can simplify a little bit. We have a constant of a out in front, and then we have these a cubes, we have the a cubed in the denominator. Well, those can simplify to give us a 1 over a squared constant out in front of the definite integral from 0 to pi over 4 of, if we now reduce what we have inside, which was a secant squared over a secant cubed, that's really 1 over secant theta, and then d theta. Let's keep this going. This is really 1 over a squared out front, times the integral from 0 to pi over 4 of, if you simplify, 1 over secant theta is really just cosine theta, then of course d theta. So it's getting better. Furthermore, we know how to integrate, we know how to anti-differentiate cosine theta, so we're pretty much there. Stuff we can do is now in picture. So let me rewrite this yet again. This is now 1 over a squared times the antiderivative of cosine theta that we know, that's really just sine theta, but we have to do this with our bounds from 0 to pi over 4. So this is turning into a pretty simple algebraic move. Let's continue on. This is 1 over a squared times, I'll use some brackets to kind of hold this together. This is now the fundamental theorem, evaluating at the upper bound minus evaluating at the lower bound, which gives us, of course, sine of pi over 4, there's the upper bound, minus sine of 0, the lower bound. So those are values we know from our basic trigonometry. Let's plug it all in. This is 1 over a squared times sine of pi over 4 is square root of 2 over 2. Sine of 0 is 0. So it's 1 over a squared times square root of 2 over 2, which is also known as the square root of 2 over 2a squared. And we can finish right there. All right, I know this has been lengthy already, but I think it's helpful to have more examples at least available to you to see explained. And the next one we want to do, number 4, is the definite integral from 0 to 1/2 of x times the square root of 1 minus 4x squared dx. Now, I put this one in here because it goes within this topic, but you also actually could have seen this integral in a much earlier topic, because sometimes, even in the context of what you're used to in the moment, which is all these trig subs, you might find one that's actually just a basic u sub trig. So like, notice the what's inside the root, the 1 minus 4x squared, the derivative of that is off by a constant, but within the problem as that first factor of x. So actually, this is just a basic u sub. I'm going to note that because it's helpful to see it and then look out for this, right? So if we let u equal what's inside the root, so 1 minus 4x squared, and then of course that would mean that du, this is just basic u sub stuff, would be negative 8x dx. Again, that's not exactly in our integrand, but it is close. We can deal with the negative 8 with no problem. So let's go back and do this. This should be much quicker to finish. Of course, now we have to have new bounds. So let's see, I'll mark this here. Our new bounds will be as follows. We had 0, but if you're plugging 0 in to the u equation, we have 1 minus 4 times 0, which of course is just 1. So the new bound instead of 0 is going to be a 1. And then we had a 1/2, but again, plug that in the same u equation, the substitution equation. That'll give us 1 minus 4 times 1/2 squared. Okay, 1/2 squared is 1/4. 4 times 1/4 is 1, so 1 minus 1 is, well, 0. So our new upper bound is now 0. Now that seems a bit out of order. We can account for that. Remember, you can always reverse the bounds by putting a negative out front, so we can deal with that no problem. Let's verify that the rest of the substitution will actually be useful here. Notice a couple things. If we're going back to the original, color coordinate this, then obviously what was underneath the square root is what we let u represent. So that'll get replaced simply by u. That's no problem. But then also notice that, let's see, that leaves behind to be replaced, let's see, the dx and the x that was in front of the root originally. Well, those are both now part of our du expression, with the added slight annoyance of this constant that's not present, this negative 8. But as you know, we can divide by -8 on both sides to deal with that, no problem. So I'm going to do that, put a -1/8 out front. That'll take care of the -8. And then that will allow me to replace the x dx with just the du. So we'll put the du out the end, and then I'll have the square root of u. Before that, of course, that's really just u to the 1/2. We'll be able to handle that pretty easily. So now, in addition to that, notice that the bounds we'd like to reverse, as mentioned, to go from low to high, and that's easily done by putting a negative out front, but we already have a negative, so if I make that positive, by pulling a negative out front, the negative will cancel, giving us 1/8 times the integral from 0 to 1. That flips the bounds for us of u to the 1/2 du. And this is ready to go. If we now do our antiderivative, this will become 1/8 times 2/3 u to the 3/2. There's the antiderivative of u to the 1/2. But we want this evaluated in our new bounds, so from 0 to 1. And go ahead and do the algebra on that, not too much trouble to do. Plug in 1 first and then plug in 0. Pretty easily turns in, I think you should get 1/12. Double check that. So in this case, it turned out to be much quicker and simpler than we had hoped, or maybe expected, I should say, because in the context of trig sub, you might think everything's a trig sub, but turns out not everything is, so look out for that. Sometimes they'll even throw a more basic u sub in the mix. All right, example number 5 is as follows. We want the integral of, the numerator is dx, and then under it in the denominator is the square root of the quantity x squared plus 2x plus 5. All right, so right away, if you start sifting through the trig sub models that we have above, you'll notice this one doesn't quite fit them because of what's underneath the root. We're not used to seeing in this case, trinomial of that form. We have usually to match it up with one of our models. So I want to show you another method you can use to get around that for this one. That is, I'm going to rewrite this as the integral of, and then I'll write it as a large fraction with just a 1 in the numerator. We'll just kind of rewrite where that dx is. We'll replace it with a 1 and put the dx at the end. And then what's under the root, we're actually going to change so that we can get this to fit our model. The way we can do it is by completing the square. So I'm going to rewrite this as x squared plus 2x, and then I'm going to say, in order to complete the square, I'll put a note about this, we're going to have to say plus 1. That will actually make a perfect square there. So let's see, a little side note here, complete the square. So I'm putting a plus 1 there. Of course, you have to compensate. You can't just change the problem like that. So though we put a plus 1, and then there already was a plus 5 after that, which we have to keep as part of the problem, then I'm going to put a minus 1 immediately to fix what I just did, all within the root. So now the root has x squared plus 2x plus 1 plus 5 minus 1. Again, the whole point is to complete the square for those first 3 terms, and then the minus 1 there is just to make sure that that is actually legit and not changing the problem. So let's now rewrite this as the integral of 1 over the square root of x plus 1 in parentheses squared. Now that's replacing those first terms under the root, and then since we had a plus 5 minus 1, that'll turn into, of course, a plus 4, and then dx. So this is now giving us something in terms of one of our models. Let's now recall, this is actually looking like the square root of u squared plus a squared model we have above. Again, you can redraw those triangles, check on them. I'll just do that slightly here. We have that as the hypotenuse, that is the u squared plus a squared under the root. The plus, remember, is in the hypotenuse only in this case, where and check those models, make sure they're lining up. You have an a in the bottom horizontal side, and then a u on the vertical side on the right. So you want to use that more in terms of these actual values, and since they're more complex, I'm going to redraw the triangle, the second triangle, which we've done before, but it helps, I think, in this one especially. So now I'm going to draw the triangle that has the actual values in. So instead of u squared, u is actually what's inside the parentheses after completing the square. So that's x plus 1, which means in the hypotenuse we have the square root of x plus 1 in parentheses squared plus 4. That's now the entire root value that's in our hypotenuse. Of course, the u value is just the x plus 1. That'll take on the right vertical side. And then the a value, in this case, since there's a 4 as the constant, we'll call that 2 squared, which means a is 2. All right, so this is giving us enough to work with to get our ratios going. But notice that this had that extra step of completing the square. Now, the rest of this is some detail that you're going to work out. I'll get the ratio started. Let's see. We'll do, for our first, we want a couple ratios, as always. The first one, which is going to involve u and a, we'll do it this way. Tangent of theta equals opposite, which is going to be x plus 1 over adjacent, which is 2. And for our second ratio, where we want to involve the root and a, of course, that's going to be then cosine. So we'll say cosine theta equals 2, that's the adjacent side, as we've already kind of noted, over the hypotenuse, which is our big root, containing x plus 1 squared, and then plus 4, all of that being under the root. All right, so we have our two ratios that we need. Now the rest is to replace and do all the trig subs. I'm skipping a little bit of detail on this one, just trying to go a little quicker since this video is now very long. So if you've hung this far, congratulations, we're almost there. But I do like to show the detail because that's often where the problems occur for people, right? So let's also then, I'm going to note, just do it right here. Note the restrictions. These matter. We've noted a couple already. But if I take this value for tangent, notice then some of the restrictions. Then we have what's under the root. That has to remain positive. So I'll just say here, check the 1-to-1. That's kind of what this is. I've been calling this step. You can also read that in the textbook as well, but check that it's 1-to-1. So what's under that root, which originally was the x squared plus 2x plus 5 in the original form, that has to be positive. Actually, it has to be greater than, greater strictly than 0 because it's in a denominator, right? So we wouldn't even say greater than or equal to because we can't let it be 0. It's being divided by, or it's doing the dividing. So that value has to be greater than or equal to 0. That actually is true everywhere. So since that's true everywhere, there are no restrictions on theta. I'll just kind of note, no restrictions on theta, because what we're using in this expression has no restrictions on x. Therefore, since we're using a theta to replace the x, there's no restrictions on theta. That's good to note. It means we're free to proceed without worrying too much about anything. Let's also take note that if we take our second ratio, the cosine theta equals 2 over that root, and if we do a little bit of flipping on that, that would imply, that second ratio, that 1/2 times cosine theta. If I just divide by 2 on both sides, I'm trying to isolate this root. Remember, we're trying to replace stuff that's in our integrand that we can't work with, and we want to use it to replace. I'm dividing both sides by 2 in this second ratio, which gives us 1/2 cosine theta equals 1 over this root, which happens to be part of that original problem, which is the root of x plus 1 squared plus 4. Okay, so that's now something we can replace. All we need left is the dx to be replaced, and then we should be good to go. So how can we get that in place? Well, notice we have the other ratio, the first one. If I just take that first ratio, which was that tangent theta equals x plus 1 over 2, we can solve that for x. In fact, doing so would tell us that x equals, if you multiply both sides by 2, you're going to get 2 tangent theta, and then subtract 1 from both sides to get x all by itself. We get x equals 2 tan theta minus 1, which means if you take the derivative with respect to theta of both sides and then multiply by d theta, that you'll get dx equals 2 times the derivative of tangent is secant squared theta, and then d theta. And then, of course, the constant term of minus 1 disappears when we take the derivative. So now we're there. We can replace dx. In fact, Let's bring that original back in to make sure this is all making enough sense. Original problem was integral of 1 over the square root of x plus 1 squared, that x plus 1 being in parentheses, and then plus 4, that's all under the root, and then dx. But what we've now discovered is that we can replace, and we'll do this with some highlighting, we have 1 over that root, which is exactly everything you see in the integrand, that can get replaced by 1/2 cosine theta. That's a huge replacement. But then secondly, we have to deal with the dx, and turns out we can. As we've also noted, the other ratio tells us dx is equal to 2 secant squared theta d theta. So all the replacing can happen as we would like. All we have left is to do it. So let's take a minute to finish. Doing the replacements, we'll say this equals 1/2 times the integral of cosine theta times 2 secant squared theta d theta. That's all just kind of replacing the stuff I've identified. Just go ahead and replace one for the other. You'll find that that's the case. And that, of course, is equal to just the integral of secant theta d theta, right? Again, do the simplification. The 1/2 cancels with the 2. Secant is 1 over cosine. Of course, that'll reduce with the cosine that we already have there. And then this is a now special integral. Let's go ahead and recall that this is equal to the natural log of the absolute value of secant theta plus tangent theta. Okay, if this is looking unfamiliar, go back and review. This is even just some basic Calc 1 stuff, or it typically is. So this is equal to this natural log of the absolute value of secant theta plus tangent theta plus c. Now, you'd think we're done, but remember, nobody cares about theta because it was not in the original problem. So you have to go back and replace using our ratios. This means we have the natural log of the absolute value of secant theta would be 1 over cosine. So using our substitution, that's the square root of the square root of x plus 1 squared plus 4 all over 2 plus tangent theta, which would be x plus 1 over 2. Again, just go back up and do these substitutions from the expressions we have from all these ratios. That's all that's happening. We're replacing secant theta with what it equals. How do we know? Because we already have that. Well, we have cosine theta. You can just flip that over. Cosine theta is equal to 2 over the root. So secant is the reverse of that, which is exactly what you're seeing now. Replace secant. Same thing with tangent. There we go. This is an acceptable answer. You might be able to rewrite that in a couple different ways algebraically, but this is just fine. We'll leave it there for now. Okay, last example, I promise. Number 6, here we go. The original is given as the integral of x times the square root of the quantity 1 minus x to the 4th dx. Now, we're going to go back up to our models. I'll move a little more quickly this time. We're going to use the model that includes the square root of a squared minus u squared. Again, just kind of double check on those models, make sure that's making sense. If you redraw the triangle on that the usual way, the bottom side is the square root of a squared minus u squared. The hypotenuse is a, the right vertical side is u, and we have those ready to roll. Let's now draw a more suitable model using this problem's actual values, which means we have theta as is. The hypotenuse is going to be 1, so that means a is 1. The denominator, the bottom horizontal side is going to be the square root of 1 minus x to the 4th. Now that's assuming, of course, that u must match x squared. And since x to the 4th is really x squared squared, that'll do. So this is our model, and I'll write out to make sure that's clear that this is using the square root of 1 minus x squared squared. So that's like 1 minus u squared, where u is x squared. Now, I like this example because it throws us off a little bit. In a second, I want to show you that. But let's first of all notice that we're going to proceed with the standard steps, which is we want our ratios. And the first one, maybe we could say, involves a u and a. So again, go back to your model. A in this case is 1, the hypotenuse. U this time is the x squared, that is the opposite. So that means we'll say that the sine of theta equals opposite, which is x squared, over the hypotenuse, which is 1. Okay, hold that there for a second. Our second ratio, which involves the root and a, will be the following. Of course, the root is the adjacent side, so we'll use cosine theta equals adjacent, which is the square root of 1 minus x to the 4th over hypotenuse, which is 1. Okay, so what's going on? Well, what you'll find is that if you try to just kind of proceed as usual, we have a little bit of a dead end here. If you go back to the original, you'll find it doesn't match. Now, I'm going to highlight this with a little frowny face because this makes us maybe a little bit upset. We've been doing so well by finding stuff that totally replaces everything in the original. But if you go back to the original here, there's this extra x value that's now showing up in our ratio as an x squared. So that's not a direct match. Everything else is okay, or somewhat. I mean, we don't have the dx yet. But so far, notice, that's not a direct match. So let's keep going to see if something else will help us move along. I think we'll be able to work around this just fine. Let's see what we can do. If I take this ratio, the first ratio we got, right, sine theta equals x squared over 1. I'm going to bring that over and just kind of verify or work on a couple things with it. And the first of those is to check the 1-to-1. So let's just check 1-to-1. Since the domain of x squared is all real numbers, negative infinity to positive infinity, and so is the domain of sine, everything works out fine there. We don't have to restrict theta at all. So that's good to note. But then secondly, in order to be able to get around the difference between the x squared we're seeing and the x we'd love to be able to replace, let's do the following. If I'm going to write out this ratio, I'm going to write it x squared on the left equals sine theta on the right. And as we're used to doing, I'm going to take the derivative of both sides. Remember, we have to be able to replace the dx somehow. We don't have it yet. So what we're going to do is take the derivative with respect to theta of both sides. So d over d theta of x squared on the left side and d over d theta of sine theta on the right side. Now, in doing this, we're basically supposing that x is some function of theta here, and you could treat this as implicit differentiation. If I take the derivative with respect to theta of x squared, that would be like the chain rule. So the outer function would be the x squared. I'm going to call that derivative 2x, but then I would multiply by the derivative of the inner function being just the x, which would be then dx d theta. Okay, again, see implicit differentiation, review that as needed. That's all that is. On the right side, d over d theta of sine theta, that's just a straight up derivative of sine is cosine theta. But now we can multiply both sides by d theta, which gives us then 2x dx on the left side equals cosine theta d theta on the right. And sure enough, this is making us much happier because now, as you can recognize, the x is in play, not the x squared, so this makes us happy. So all we had to do was kind of proceed as usual. There's another way, I think, to address this. You could use like an extra substitution. I've seen things like this done that way. It's honestly, I think, more work than it's worth, but it's a possibility. So now that we have what we need, let's see if we can go back and actually replace everything. That's ultimately the goal, right? So I'm going to bring back the original. What was the original? I can find it. Oh yeah, it was, the integral was x times the square root of 1 minus x to the 4th, and then that was dx. So let's see, can we replace all of these pieces? Well, I believe so. In fact, let's do a little bit more work to make this extra clear on what we were just doing. If I divide both sides by 2 from where we were just working, that would leave it as x dx equals 1/2 cosine theta d theta. So now we're in business because the x can get replaced. So in fact, let's do this. In fact, I'll keep the same highlight color I've been using. There's the x, and we're going to replace the x we see with it. But not only that, now we also have a way to replace the dx, and that has to get replaced as well. But back up, and you can see the rest falls together nicely. We have to replace the square root of 1 minus x to the fourth, and sure enough, we have that expression equal to, well, cosine theta. So let's do this replacement and see if everything just kind of finishes off for us nicely. This will then turn into the integral of, so instead of the x dx, we're going to replace that with a 1/2, which I'll put out front, and then cosine theta d theta. But let me slide things over because we have a little bit more to put in there. I'm going to put the d theta with a little space because that space has to be replaced with the root getting replaced with cosine theta. So that's that square root of 1 minus x to the fourth getting replaced with cosine, as we said it's all equal to, which gives us at this point 1/2. Let me rewrite this. We got 1/2 times the integral of cosine squared theta d theta. Okay, so now can we go from here, right? Can you take the antiderivative of cosine squared? Maybe not quite, but we actually know enough to get around that also. So let's see. I can bring this. Let me just pick on color we haven't used yet, and let's say recall the power reducing formula. We've used this recently. What it means is that cosine squared, I'll just use the letter x to look separate here, but the cosine squared of x is equal to 1/2 times 1 plus cosine of 2x. This is just a power reducing formula. We've used it recently, and it can apply to reduce the power of our cosine expression so that it's actually doable with familiar things. So let's go ahead and then rewrite this as 1/2 times, now here we go, instead of cosine squared of x, I'm going to write it, and I'll even use the replacement I was using. Actually, let me get my integral symbol there first, and then we're going to write this as 1/2 times parentheses containing 1 plus cosine 2x, and then we want this as d, sorry, actually we're using theta here, so d theta, sorry, not x. X was my little formula variable. Be careful, this is a theta. So using the power reducing identity, fine, great, but make sure to use the right variable. In this case, it's a theta. All right, so there we have it. We're getting closer to something we can do. So let's proceed. If I take this a step further, let's see, I'm running out of space. I'll write this as 1/4. If you multiply those 1/2s together, you'll get a 1/4 times the integral of, I'll put it in parentheses, 1 plus cosine of 2 theta d theta. Well, this is something that is doable. Let's proceed a little bit further. See if I can squeeze it all in here. This is just equal to, actually we can do this by now, right? So the 1/4 times the 1 is really 1/4. The antiderivative of that would be theta, so we'll call that theta over 4 as the first term antiderivative. Okay, and then proceed, so plus, we'll have another 1/4 because we're distributing that 1/4 into all the terms here. The antiderivative of cosine of 2 theta, well, this is now something we could do. The antiderivative of cosine would be sine, so this would be, let's see, sine of 2 theta, but that would be, of course, off by a constant to the antiderivative, so you'd have a 1/2 floating in front of that. Okay, so ultimately here, let's put this together. We have theta over 4 plus 1/8 times sine of 2 theta. Well, that's an identity. That's just 2 sine theta cosine theta. It's a double angle identity from trig. And recall that we know sine theta above. In fact, oh, let's see, do I have this all highlighted? Yes. So sine theta was originally x squared. Let me just highlight that to reference where we're coming from. Sine theta was really just an x squared. And then cosine theta we had somewhere as well. That was the blue highlight, that root that we had previously. Let me put that in. So those are going to get replaced, as well as theta. So theta, notice, if you know that cosine theta equals the square root of 1 minus x to the fourth, or, more simply, let's say the first ratio, sine theta equals x squared, then you could say that theta is the arc sine of x squared. So let's just put that all in place. This means, ultimately, we have 1/4 times the arc sine of x squared. So that's replacing theta with arc sine of x squared coming up from the ratio above, and then plus 1/8 times 2 would be 1/4, and then we'll replace sine theta and cosine theta with what they're equal to above, which will give us an x squared times the square root of 1 minus x to the fourth, and plus c. Okay, that was a long, lengthy explanation of this trig sub topic, but I hope that these examples give you stuff to work with. Right? That's the whole point. The details are what matter, so watch it as much as you need, and hope it helps.